In this video, we're going to take a look at some basic probability examples. Now, there are two ways of assigning probability. The first approach is what's called the classical approach to probability. Now, in that technique, we assume that we can construct the sample space for an experiment in such a way that each outcome from that sample space is equally likely to occur. That's very important. And we also count all the possible ways that event A can occur in the sample space. Then the probability of event A occurring is defined to be the number of ways A can occur divided by the number of outcomes in the sample space that you constructed. So that's the first technique. Now, the second approach that we'll consider is the empirical approach to probability. Now, in this case, we can't really construct the sample space for an experiment. It might be too difficult to do that. In which case, we conduct the experiment many times, and we count in that many times how many times the event A occurred. Then the probability of event A occurring is approximated as the number of times event A occurred divided by the number of times the experiment was conducted. So that's the empirical approach. So let's take a look at a few examples involving these two techniques. For our first example here, we want to consider the experiment of rolling a six-sided die. And we want to calculate the probability that an even number of spots appears on the side face up. So we can easily enumerate our sample space for this experiment. The sample space is just going to be the outcomes 1, 2, 3, 4, 5, 6. And you notice that for a fair die, all of these outcomes are equally likely to occur. A 2 is just as likely to occur as a 6 is, as is a 4, and so on. Now, the event A of getting an even number consists of the 2, 4, and 6. So there are three ways that event A can occur, and so the probability is going to be 3 divided by 6 using the classical approach, and so we have a probability of 0.5, or if you convert that into a percent, 50%. So that's our probability for getting an even number when you roll a six-sided die. Now let's consider two more classical probability examples. Now, before we do these two examples, we need to understand how a deck of cards is organized. So a standard deck of cards consists of 52 cards with 4 suits, diamonds, hearts, clubs, spades, and 13 ranks. For example, this graphic here might help. So here's a standard deck of cards. And you notice that you have 4 suits right here. Clubs, spades, hearts, diamonds. And then you have 13 ranks. So you'll have 13 clubs, 13 spades, 13 hearts, and 13 diamonds. Now, going back to our example then, for our first problem, we assume that we have a well-shuffled deck of cards and we select one card at random. What is the probability of selecting a king? That's what we want to calculate. Well, there are 52 cards in the deck, and each card has an equal likelihood of being drawn. So the size of our sample space is 52, and the number of kings in the deck is 4. We have 4 kings in the deck of cards. So the probability of drawing a king is going to be 4. That's the number of kings in the deck divided by 52, the total number of possible outcomes we could get. And 4 divided by 52 is 0.0769. Or approximately 8% if you convert this into a percent by multiplying by 100. In this example here, we want to ask ourselves, what is the probability of selecting a diamond? Well, same procedure. The number of possible outcomes is 52. That's the size of our sample space. Of these 52, every card has an equal likelihood of being drawn. And in this 52, there are 13 diamonds. So the probability of drawing a diamond is going to be 13, the number of ways you could get a diamond, divided by 52. And that's actually exactly equal to 0.25 or 25%. Notice once again in the graphic here, if we look at this graphic, for the first example, we have 4 kings in a deck of cards. Every card has an equal likelihood of being drawn, and so our probability for the first example was 4 out of 52. For the next one, we wanted to know the probability of drawing a diamond, and you notice that there are 13 diamonds in a deck of cards. And so the probability of getting one of these diamonds is going to be 13 divided by the number of cards you have, 52. So 13 divided by 52, and that's the probability of drawing a diamond in a deck of cards. Now let's take a look at a few examples involving the empirical approach to probability. Now, for the empirical probability technique, you're usually faced with a problem where you can't really enumerate the sample space. The two problems that we just looked at, rolling a die and drawing a card from a deck of cards, we could easily enumerate what the sample space was and how big it was. But for these problems, we'll see, we can't really do that. So we're left with just conducting the experiment many, many times and then counting how many times did event A occur. So for the first example here, the historical record of weather in Philadelphia indicates in the last 125 years there's been a measurable snowfall 11 times on Christmas, December 25th. Let's estimate the probability that it will snow on Christmas next year. Well, by the empirical rule, think of it like this. The 125 represents how many times the experiment was conducted. For the last 125 years, we noted whether or not it snowed on Christmas. That's our experiment. So we conducted the experiment 125 times. Out of that 125 times, it snowed 11 times. So we can estimate the probability that it will snow on December 25th in Philadelphia next year to be 11 divided by 125, or 0.088. That's our probability. And if we convert that to a percent, that would be approximately a 9% chance. Let's take a look at this one. So here we have a baseball problem. So a baseball player has been at bat 585 times this season and got a hit 135 times. Estimate the probability that at their next at bat, the player gets a hit. Well, this 585 represents the number of times the experiment was conducted, and the 135 represents the number of times event A occurred, event A being getting a hit. And so based on this, we can estimate that the probability they get a hit the next time at bat is going to be 135 divided by 585, the number of times event A occurred, which is getting a hit, divided by the number of times the experiment was conducted. That's every time the player got up to bat. And 135 over 585 is approximately 0.231. or as a percent, approximately a 23% chance that the player will get a hit next time at bat. And by the way, this value 0.231 is also called a player's batting average. So every time you hear a player's batting average mentioned in baseball, that's how it's calculated. It's calculated as an empirical probability. Now in our next example, we're going to look at using tree diagrams to help us find a probability. So in this example, we have a couple and they plan to have 3 children. We want to find out what is the probability that they have at least one girl. Now for this problem, we're going to assume that the probability of having a boy is the same as the probability of having a girl, so each is 0.5 or a 50% chance. So to solve this problem, we're going to draw a tree diagram as we have illustrated right here. So what we do is we start out, and for their first child, we have 2 branches drawn representing the possible outcomes for the first child. They can have either a boy or a girl, and each probability is the same. Now after they have their first child, if they had a boy, they can then have a boy or a girl for the second child. And once they have the second child, they can then have either a boy or a girl for the third child. So each path in this tree diagram running from top to bottom represents one possible outcome. So you see they could have a boy, boy, boy. Or they could have a boy, boy, girl. Or they could have a boy, girl, boy, and so on. Now you'll notice that there are 8 possible paths going from top to bottom. You see, if you look at the bottom row here, you see that there are 8 labels down here. 1, 2, 3, 4, 5, 6, 7, 8. Now each path has the same likelihood of occurrence. So each of these outcomes up here have the same likelihood of occurrence, and there are 8 possible paths. And if we look at the paths, we see that 7 out of the 8 paths have the outcome of having at least one girl. Notice, like with this path right here, there's a boy, boy, girl. And then with another path, we have a boy, girl, boy, boy, girl, 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 boy, boy, and so on. And there's only one path where you don't have any girls, and that would be the first one over here, boy, boy, boy. Now, each path running from top to bottom has the same likelihood of occurrence, and so the probability that they have at least one girl is going to be 7 out of 8. And correspondingly, the probability of having all boys would be 1 out of 8. And so we see the answer to our problem is the probability of at least one girl is 7 out of 8. And that's how a tree diagram can help us find a probability. Now later on, as we go through the course, we'll see that we can solve this problem without using a tree diagram. So we'll be able to solve this problem using what's known as the complement and multiplication rules, in which case we won't have to draw a tree diagram. But a tree diagram is helpful to understand graphically what's going on in a problem.